Hi, welcome back to this video series on cryptography. In this segment, we will learn how to construct a pseudo-random permutation. It is sometimes called block cipher as well. This is based on the idea of Feistel network. In this segment, I will be using the Feistel network to construct a pseudo-random permutation. It is going to build upon what we learned in the previous segment. We used pseudo-random functions using pseudo-random generators. In this segment, we will be using pseudo-random functions to build pseudo-random permutations. There's a lot of pseudo-randomness here. Okay, so my goal is to show to you how to build PRP, pseudo-random permutations, right, using pseudo-random functions under the hood. I will be using a particular construction called Feistel network, which is one of the novel ideas in modern cryptography. So in the previous segment, we learned about how to construct PRF, pseudo-random functions. So there is one problem with PRF. PRF is not necessarily invertible. Okay, so it is like a one-way function. Okay, from a computational point of view, it is a one-way function. So given the output of PRF, it will be difficult to find the input. PRF is more or less like a random function by definition, other than that. Okay. So how do we now construct functions that are reversible, like a one-one function? Suppose our goal is to build functions where you have a domain, right? Domain means an input set, basically, set of points, and the range is another set of points, right? What we wanted to be able to do is we want to be able to construct permutations, meaning functions that are 1, 1, and on 2. Okay, so something like this. We want to be able to construct such a function. Okay, it's of course this is also keyed function, right? So our goal is to build. Let me call this PRP. PRP. Sometimes people also use FK. Okay, and I will differentiate between FK when I refer to PRP and PRF. Okay, so it becomes more clear. Or it's also better to use PRP directly, like this notation. Okay, what I'm going to do is simply call PRP, right, pseudo-random permutation, which takes some data X that you would like to encrypt, and it is also keyed. Okay, so what makes a PRP useful in cryptography is that this PRP should be indistinguishable from a truly random permutation. You know, from the space of all functions, you pick one to one function. That random function is pretty much the same as the PRP that we defined here. That's the definition of PRP in cryptography. It should not be distinguishable from a truly random permutation. Okay. All right. So we do know how to construct PRF. We learned in the previous segment, right? PRF, what it does is it takes X as an input and gives us some random looking output, which is not necessarily distinguishable easily from, which should not be distinguishable easily from a truly random function. Okay. Remember, this need not be invertible. This need not be invertible. Okay. PRFs need not be invertible, but the PRP are invertible. So for example, you can imagine something like AES, very informally speaking, can be viewed as something like PRP. Okay, it's a weaker climb. I'm not going into the details of AES in this segment, but something like that. You know, you can encrypt, you can also decrypt. Okay, so you need a 1, 1, and on 2 function. All right, with that background, I'm going to talk about a Feistel network, right? So how do we construct Feistel network? So Feistel network has a very nice recursive structure. So let me explain the structure. So we have, say, a block, right? Let's assume a block is, say, made of 128-bit data. Okay, so there are 128 bits of data that you can put inside this particular block. Okay, so we divide this into 2 halves. Let's call this block L0, the left half, right? And this is the right half. So left half will be made of 64-bit, right half is made of another 64-bit. Okay. So what we do is that we take pseudo-random function. Okay. We call the pseudo-random function F, the key is K1. Okay, so let me be more clear. This is important part. We need one master key, of course, right? Master key K, but then we derive bunch of round keys. Okay, from this key we can derive bunch of keys. You can use key derivation function. I'm going to use a pseudorandom generator for this purpose. Takes the key K and gives me, say I am going to do 4 rounds and I will get 4 keys and so on. Okay, so anyway, so let's assume we have a way to take the master key and generate bunch of keys from that. So for us, we need to call the pseudorandom function f. For the first round, we will use the key K1. Okay, that's the goal of the pseudorandom function box here. Okay, we need to pass the input. What is the input to the pseudorandom function? The right half, meaning R0, will go as an input to the pseudorandom function. It's going to give some gibberish, right? That's the definition of pseudorandom function. That gibberish is like a key, like we talked about one-time pseudo one-time computation. And now we will feed that into an XOR box. Okay, say I have an XOR box here, right? That XOR box is going to take my output from the left half and feed it to my XOR, right? So what will happen now is that I will get out some gibberish now because of the definition of XOR, and that gibberish is going to the next round. Okay, and there's one more thing I need to explain. The R0 is also copied as it is to the next round. So the right half of the previous round is copied as it is to the next round. Okay, and that becomes the input to the next round, and this process continues. This is, we call it L1, right? And this becomes R1. Okay, what will we do with this now? Let me explain one more round. We take, again, we call the pseudorandom function f, right? We evaluate using the second key, and we do the same now. We feed this data, right, to this, and we also copy as it is to the next round. L2 is same as R1. And we take this output, right? We XOR it with the L1 block, and we get some gibberish out, and we pass that to the next round. Okay, so that's basically how we get the Feistel network working. Okay, so if I stop it here, like I only did 2 rounds, this is insecure, and I will talk about why it is insecure later. Just take it for faith now. Okay, so the cryptography research literature has proved that you would need 4 rounds to make a pseudorandom permutation secure. So you can draw this picture 2 more times, meaning total four rounds, right? Then you will have the final output. That is basically the output of the encryption process. Okay, here is your data. The data is L0, R0. 128-bit data is split into 2 halves, and it goes through this process with mixing it with pseudorandom function, and we do it 4 times. We get some gibberish out. I'm going to show to you those things in a moment. Okay, more concretely using a demo. So this is basically it. So we can actually algebraically write this syntax, right? How do we get the output of ith round? So Li is same as Ri minus 1. L1 is same as R0. So we can generalize that. And Ri is same as, how do we get Ri? We take Li minus 1, right? XOR it with F. We take the ith key, right? And we feed in Ri minus 1. Okay, this is basically it from an encryption perspective. Decryption is easy. Remember, our goal is to construct PRP. That means we should be able to go back from the last round. For example, let's take this only one round. Okay, let me show to you how we can do decryption. This is encryption. Decryption is easy. Let's say we are given L1 and R1. Our goal is to go to L0, R0. How do we do that? We know L1 can be exactly copied to R0. So let me clarify this. This is encryption and this is decryption. Okay, so let me write the decryption circuit. L1, right? You copy L1, and so you got R0 now. Okay, you know why we cannot stop at one round now, because you are leaking the right half of the data right away. So if you stop Feistel network after one round, okay. So R0 is L1. What about L0? L0 we can easily reconstruct. We take R1, right? And we XOR it with FK1 of R0. Okay. If you know the properties of XOR, you can confirm and verify later, but essentially this R0, this is R1. We XOR it with R0 CFK. That means we will get exactly this point, and which is nothing but L0. So it's easy to go backwards now. So here is a construction which is both 1-1 and reversible. Okay, it's all defined in terms of an attacker who can only run polynomial times. Okay, so if we allow the attackers to run exponential time, they can break any scheme. So cryptography usually is defined by allowing attacker running his attacks on polynomial time. Okay, only a polynomial number of queries are allowed. Okay, so anyway, that's an extra piece of information. So we have the encryption and decryption ready, which means we are done with the construction of PRP. So we know how to take a PRF and construct a PRP. PRP is also equivalently called block cipher. Okay, so I'm going to show to you this idea in action so you get a concrete understanding. One thing I would like to call out before the demo is that we don't need to construct two different programs for encryption and decryption. We can use the same program for both encryption and decryption. Okay, the way it will work is that, let's say after you're done with 4 rounds, you take L3 and R3, which is the output of the last round, right? You swap them. So your L3 becomes R3, your R3 becomes L3. And then instead of starting the keys from K1, K2, you start from the end. So because remember, the last round was encrypted using, say, if I use K1, that the last round must have been encrypted with K4, right? If I have 4 rounds. So we should start from 4th key, 3rd key, 2nd key, and 1st key. So that's basically it. That means using only one program, we can do both encryption and decryption. Okay. Essentially, at the end of encryption process, just swap the left and right blocks, and then during decryption, use the same encryption program, but don't start from key K1, start from the last key onwards. This way we will get back to L0 or 0. That's what I did in my implementation. Okay, I didn't define this logic at all. I only used encryption to do both encryption and decryption. Okay, all right, let's do that now. Let's go to a program and to play with it a little bit. So what we are going to see is hopefully interesting for you. Let me walk through the core ideas first, not going to all the fine-grained programming level details. Okay, so I generate a master random key, right? 256-bit key for demo purpose, which is pretty good. 256 keys are not easy to break in a symmetric cryptographic context. And then I'm going to take a 256 block cipher. Actually, most of the block ciphers that are used today are 128-bit, but since we are using the pseudorandom function as the kind of the way to realize PRP, it's okay to use 256. Okay, usually it's 128-bit, the block lengths. Okay. Now I'm going to generate some random data to encrypt. So my data itself is random. I have no structure in it. I just randomly generate it. I'm printing it for the sake of showing to you in binary. Then I'm going to call my encrypt function, which will encrypt the data using this key. Okay, and I'm telling what is the block length. Block length is 256-bit block length. Okay, so my data will be split it into 2 halves, 128 and 128, right? That's what the Feistel network structure is. And then I decrypt it, and then I assert that the decryption is better be equal to my data. So that's basically it. Okay, now let's look into the details of encryption a little bit. How am I doing encryption? I take my block length, which is say in this case 256, and I divide it by 2, which means my individual keys are 128-bit keys, right? Remember my Feistel network diagram. I had partition my input block cipher into 2 halves, and then I take my right half and XOR it with, I feed the right half into my into my pseudorandom function, which requires another key. So I need a round key. That's why I generate the round keys here. Bunch of round keys are generated, and then I'm calling the Feistel network to do the encryption of my data. Okay. Each round key is basically 128-bit because our data, the whole block is 256. We split it into two halves because we need to do XOR of the output coming from the pseudorandom function. Okay, that's the reason I do that way. Okay, now we have a Feistel network which we will do round number of times, and then we will swap the last output because of the way I wanted to decrypt. The decryption process is exactly the same as encryption, as I said. I, of course, have to derive the round keys from the given key. If encryption and decryption are done by two different parties, both of them have to derive the round keys, right? From the master key. They have to have the same master key. And then we do the Feistel network, but in the reverse, okay? Because we want to go all the way up. Reverse meaning we will use the last key first, and then all the way to the first key, okay? And then we swap the output again to get exactly the same data that was originally encrypted, okay? Because we did a swap at the beginning, okay? That's why we need to do it also at the end, okay? All right, so this is basically it. Now I'll show you the basics of the Feistel network. So the Feistel network itself is programmed here. All I'm doing is I take my key, which is the one particular round key, not to be confused with the master key, right? I split it into two halves. That's happening here, right? The data is split it into two halves. My data is called X here. I get the left half and the right half, right? This is basically the conversion of left and right, taking the first half and then the next half. This is the Python syntax. And then we generate the key stream using the pseudorandom function, and we XOR the left half of the data with the key stream, and the left of the output is same as the right half, right? That's how Feistel network works. And basically then the rest is just convert this into a byte array, a bit array, and then send it to the caller. Okay, that's all. So very simple. Okay, let's see a demo quickly and then we wrap it up. So I'm going to reduce the key size significantly for demo purpose. You should not be doing that in production, of course. So I'm going to make it so small that it will fit easily for us. Okay, let me quickly run this thing one moment. It's going to run now. Okay, there's a lot of data. So I'll reduce the key size, right? To very simple. Oh, can't edit. One moment to reload this thing. And I'm going to do it only one round, which is not at all secure. But I will first show one round and then increase to 4 rounds. Okay, so I'll be constructing Feistel network in a moment, and then we will talk about the output, and then we can compare all the drawings that I did on the whiteboard with the actual output. So let's do this. Let's do a simple demo, right? Take only 32-bit master key, and let's take a 64-bit block. Okay, so it means our block can hold, or even more smaller. I'm going to make it smaller, 32-bit. Okay, so we are going to have a very small block. 32-bit random block will be generated, and then we will do encryption and decryption of that. This is not important for us. So we're generating, yeah. So first step is to show to you, here is our 32-bit data that we want to encrypt. It's shown in binary. There's nothing confidential. There's nothing novel here. I'm just selecting a random 32-bit data. And I mentioned to you, we split this into two halves, the left half and the right half. Okay, the right half is basically all the things that you're seeing here, right? 1, 1, 0, 1, 1, 1, and all of these. That's exactly what you're seeing here. This is the right half, which is 16-bit, and then the remaining 60 need not be 16 if you count it, but that's how Python, you don't have to put a 0 in the front. So you have another 16 bits if you put additional zeros in the front. Okay, so here is your left half and the right half. And then the key stream is generated based on pseudorandom function, right? Which takes the random 32-bit key and derives a new key, which is 16-bit key in our case. XOR that with the left part, right? Remember, the left part gets XORed with the key stream, and then we get a ciphertext. Okay, but if you look at the ciphertext that comes out of the first round, it's bad because it has the exact copy of one of the blocks. Okay, that's how the Feistel network is structured anyways, right? You can figure out which part is coming. Remember, the right part is not at all modified. So during the first round, that means the right part should be part of the ciphertext as it is. So we can confirm that easily. Look at here, 111 0 0. All of this part is exactly over here. Okay, maybe I was selecting too much. Just give me a minute. We take the key stream, we XOR it with the left, and we copy the right as it is, right? But then we also did a swap for the decryption to work. That means the right part we should be able to figure out easily. I need to see the 11011 or 111011, this part, 1000. I think this is where it is. So see here, the right part. Here it is. This is basically it. This is bad because you have a copy of the data as part of the ciphertext. That's because we just did only one round. And I did an assert statement at the end, so you can be confident that the program is doing what it's supposed to do. It's just a proof of concept demo anyways, but still, I put an assert statement to show decrypted data is same as the encrypted data, the plain text data. Okay, so we can see that one round is terrible. Actually, it will take a little bit more time to show to you that 2 rounds is also terrible. So I will use 4 rounds now as described in cryptography literature, and I will do much larger key size. Of course, I will take 256-bit key, and I will take a 128-bit block cipher. And now let's try. You see a lot of outputs, and we cannot go through all of them because we're doing the same Feistel network 4 times, and each time I'm printing the output to just for my own debugging purposes. Okay. Anyway, so what we learned is that we can do encryption as well as decryption using Feistel network. And the Feistel network is a permutation in this case, which has lots of application. The Feistel network has lots of applications in cryptography. It is used in the design of DES, one of the very first or famous encryption standard. It's not recommended today, but it's one of the building blocks for the modern cryptography world. It's also, the Feistel network is also used in RSA for padding purposes. If you don't know RSA, that's not a problem. But I would like to call out the design pattern of the Feistel network for your attention. So what we learned today is that we learned how to construct PRP from PRF, right? All we did is essentially use the PRF under the hood, right? We take the master key and we derived a bunch of keys, and I used the PRG for that purpose. And in practice, we have to use key derivation functions that take one key and produces a bunch of keys, but I used PRG, which is perfectly fine also. This case is very slow, of course, but I used the number theory based PRGs, the Bloom-Shoup generator. Okay, that's what I did. And then I used that PRG to construct a PRF that was the part of the previous demo. And this demo, I used the PRF. This is the PRF, right? And I constructed a Feistel network, which turned out to be a PRP. Okay, that's all. So we know how to do all of these symmetric cryptographic operations just using one-way functions. And we treat one-way functions exist. We treat some of the hard number theory problems as one-way functions. From the one-way functions, so this is the map we have been through. So we have one-way functions. When I say we have one-way functions, I mean to say we have we make an assumption. This is not conditional. This is not unconditional. Okay, we make an assumption that factoring of numbers is hard, and that kind of problems we assume. So we take one-way functions. We assume one-way functions exist, and we built pseudo-random generators on top of that, right? PRG, and we use PRG to construct a PRF. Okay, PRF. And we used PRF actually to build stream ciphers. In the previous demo, I shown you how to construct a stream cipher from a PRF. Okay, stream ciphers, like the one that is used in counter mode and so on. This is the basic idea, stream ciphers. Okay, and we today used PRF to build PRP, which is the pseudorandom permutation, like invertible functions using Feistel network as the underlying structure. And this is basically called block ciphers. Okay, the funny thing is, or the amazing thing for me is that all of this is done using number theory based problems. Okay, you could generalize it to anything like lattice based cryptography or whatever. As long as we have one-way functions, we have pseudorandom generators, and we can build pseudorandom functions, and we can build PRP. But this is one mostly theoretical. In practice, we don't really follow this flow. Not many symmetric key cryptography systems built based on number theory problems. They mostly built on the XOR properties, permutations and substitution, that kind of thing is used in symmetric key cryptography. But it's very interesting to see that the number theory hardness problems like quadratic residues and one-way function, they provide the foundation for even symmetric key cryptography constructions. Okay, that's basically it. Thank you for your attention.